Good morning, everybody. I'm sorry to not be here with you this morning, but it's a bit late in France now. Just to introduce myself, I'm Renan Le Roux. I'm a research engineer at INRAE in the unit Agroclim, working in Avignon. And I'm working on the impact of climate change on different agricultural system, and I will present you some of the result and some research we may conduct in the ERL project. So why using agroclimatic indicators in climate change studies? One of the first um, idea is because agroclimatic indicators are quite easy to compute from from climate data, for example, from climate data produced in the part one, especially with fine scale climate data. And using this indicator, we are able to estimate agroclimatic condition, for example, water balance with different climate model and different climate scenario at different temporal scale to estimate how climatic condition will evolve in the future in agricultural systems. We can also estimate specific risk for different crops and how this risk can evolve in the future depending of the climate scenario and climate model. And these kind of indicators are quite interesting because they can be combined and applied for various agricultural systems such as crop, livestock, and grassland, and are quite useful for territory analysis and to have an overview of agricultural territory. So we now use two main kind of indicators. The first one is the most famous one, is the most used one is the agroclimatic indicators. So you compute an indicators at between two dates every year. For example, the number of day of frost during the April months. And every year you compute the number of day of frost between the 1st of April and the 30th of April. And you can look how this frost event may evolve in the future or in different region. It's quite useful to compare different geographical area and to estimate, for example, suitability of a crop inside an area and compare how both area can be suitable or not for a crop. And the second approach is the ecoclimatic indicators, which are now based in phenological stages. So you need to compute the phenological model, and then you look at case stages, for example, bud break to flowering, and you'll compute the number of day of frost between bud break and flowering every year. So the date of the computation are different, but you always focus on the case stage and the sensitive stage um, of the crop for this kind of event. Another Another important topic is the importance of the spatio-temporal resolution using agroclimatic indicator, and we work a lot on that in the past few years, especially at very fine scale. Here you've got the same index, so your Euglena index, which is index computed for agroclimatic condition of vine and wine production. And on the right side, you've got a European map for the Junglen Index at the end of the century with one climate model. And you can see that there is a lot of variation in Europe, of course, of this kind of index. But the interesting thing on this plot is if we take just one cell of the 50K climate model and you do some very fine scale modeling, we did it during the Life at Viclim project, you can produce very fine scale map, which is 100 meters map here for different years. And if we look at the inside this small area near Saint-Emilion, you've got a lot of variation of the Euglena index inside a very, very small area. And also you've got a lot of variation between years. And this is And it's quite important to take account about the internal variability of spatial, but also temporal variability of this kind of index to adapt to climate change. Another important thing is to include phenology in the agriculture, in the computation of the indicators. Here on the left, you've got the evolution of phenology for wheat in the future, and you see that it's moving, shifting earlier and earlier in the growing season, and this kind of can be exploited with for adaptation because it can allow you to avoid some. For example, some heat wave at the beginning of the summer. If you take earlier varieties, you can avoid some damage. On the right side, you've got an illustration of this depending of the species for vine. So you've got the Syrah and the Uni Blanc, which are two varieties of vine. And if you look at the water balance and the evolution of water balance in the future, you've got less problematic water balance deficit, or less water balance deficit for Uni Blanc in the future compared to Sierra, especially for the RCP 8, 8.5. And another important topic showing in this plot is the agreement, the need to agreement in the model, because depending of the climate model you use, you won't have the same evolution of the climate, and for adaptation you need to be confident in the climate projection, and we're working a lot on how to represent, estimate, and mitigate the uncertainties for adaptation of crop. With the ecoclimatic indicators, so including the phenology, you can also look at which stage, which event you can relate which stage with a specific event, and then you can propose to growers how to adapt to very specific for example, here for wheat, you've got at the beginning of the growing season, the main problem is the water balance. Um, is the water balance, and at the end of the season, the main risk comes from heat waves and drought, and it's getting worse in the future, especially in the far future. But decomposing all the season, the different risk, it allows to adapt at very fine scale during the growing season, how to adapt to climate change. A quite new methodology we developed inside the Agri4Adapt and inside the PhD thesis of Maël Aubry, which I supervised. It's the how to estimate the accident probability of risk. So here it's the probability that two risks arrived the same year and compared to the 10% worst year we've got in the past. So if you go for an example here in the north of France, you can see that having some heat during the flowering and a drought during at the end of the cycle, so both combined at the same time, we start from almost 1 year every 30 or 50 years to 1 year every 7 or 8 years at the end of the century. And this kind of combined risk are really a big issue for growers, because it's when you've got some combined risk, but you've got the most problematic years. And this kind of method has been applied to New Zealand vine during a mile visiting the last 3 months. We already have some ongoing work inside the laboratory and inside the Agri4Adapt project. For example, with some colleagues from UC who are working on how the resolution of a climate model may impact the result of agroclimatic indicators. Here is for frost day. We compare the 3 kilometers WRF model in the Marlborough region. I think you will go here in the next few days. So Blenheim is here. and the WRF model at 1 kilometer, and you can see that refining the resolution, you can identify some area free of frost or some area concerned frost, but not um, detected by the 3 kilometers model. So working at fine scale, it's very quite important to have a good evaluation of the different risk for crops. And then the last work I can present you is the new with the new dataset produced by Meteorfence in New Caledonia. We start to estimate how climate change may have influence or impact the agricultural sector of New Caledonia. And here the first result of the trend in precipitation for the last 35 years. And you see that during the rainy season in December, January, and February, we've got a rise on the precipitation, and contrary to the dry season, with getting drier and drier, especially it's significant in the center of the island. So it's kind of work we will try to investigate more because the data set is quite new and there's not lot of work on it. So thank you for your attention. If you have any question, you can send me any email, or I'm sure Hervé can answer most of them. And thank you for your attention, and sorry again to not be today.